Thank you everybody for inviting me to be here. Thanks for Charles, John, all the organizers. Thanks Ben as chairperson for this session. It's a great pleasure for me to be here. So I'm here, I'm talking something about disease control and emerging threats. So my talk, though the slides will, mixed, but two key points, take-home message. First, on behalf of China CDC, we will work together with you, all the African people here, Africa CDC, and the regional offices. We will work together with you, fighting against any diseases, any public health problems. That's the first message I want to give you. A second message, so though I'm the Director General of China CDC, but I want to tell you, I am still a scientist. So I want to give you my view as a scientist, what we can do to tackle these emerging threats. So it must be based on science, must be based on surveillance. So basic science research and surveillance is the key to solve this emerging viruses threat. So that give me 25 minutes. I've hopefully finished up with the time. So public health in the global setting, as you know, so the viruses and public health problems always there. So we have to face together. There's no border for any viruses. The distance between one virus to a new country is just one flight distance. Overnight, I came here for 12 hours. If there's any viruses can come with me, landed here early this morning. Last night in China, but early morning will be here in Ethiopia. So that's the distance. So this is why we have to work together. Good example is the MERS in South Korea. So that was in 2015. So one traveler came back to South Africa with 186 cases, including the original case, index case. One guy traveled to China, one Korean traveled to China with that single case in China due to the lessons we learned from the SARS. So we isolated this case, we got him cured and treated well, and he recovered. We don't have any further cases. So that tells you, if you build up very good surveillance system, if you have very good facilities, if you have very good awareness of the public, if you have very good facilities to treat for the treatment, you are okay. But if you don't, you had something like SARS in China, you had something in South Korea with a single imported case, 186 cases with 39 death cases. That's the situation. So this is why we have to work together. Ebola, DRC, at the moment, everybody knows. I want to remind you, that's the basis for the talk, for the work. We have to work together. Then Lassa fever in Nigeria. So it's so obvious. I hope if you are not in the field, remind you. That's what important. If you already know this, that show you very quickly. Flu. So flu is one of the oldest viruses we ever encountered for human beings, but one of the most difficult viruses for us to tackle. So I was asked by my boss, by the public, hey George, can you really do something for the flu? Why do we have flu every season? Every year, 2 seasons for this flu. Why don't we solve the problem like we eradicate smallpox, like we get controlled for the polios? Why don't we do the work like the hepatitis B virus, almost relatively well controlled inside China? Why you cannot do anything for the flu? That's because flu is flu. That's a very good answer. Why flu is flu? Because flu has a very broad spectrum of the host. So that's the problem. You look at here, you see flu. This is the flu for A, B, C, and D. And also, more importantly, even for the flu A, you have 18HA, you have 11NA. If you put the bad H16, H70 out, and then the H70, H80 cells out, N10, N11 out, you still have 16 plus 9. If they times together, you are facing 144 subtypes of flu. More importantly, it can be carried by the microbe birds. From time to time, you have an avian flu, as Ab Osterhaus is here, maybe he's somewhere there, but he's this building. But he did a lot of work. It could be the problem with some, sea animals, mammals. So because they have very broad spectrum of the hosts, so we have the problem. So how can we solve this problem? We have to work very hard, do the basic research, make sure we understand why we couldn't control those viruses. They have very broad spectrum of the hosts. Why we eradicated the smallpox with a single host. Why we get very well, almost eradicated, almost, polios. And hepatitis B virus in South China, we used to have 15% in the population, 15%. 15 in 100% in China when I was a boy. But now we have 3 in 1,000. If anyone who is under 5 years old, because of vaccination. So vaccination is good, but it can only do something for some virus, not for the flu. So because we know it's a very broad spectrum of the host, and also we don't understand well for the flu. So this is actually what's the problem we are encountering. The next question, why do we have so many questions? How we encounter so many viruses? And what's wrong with our human beings? That's the question we should keep asking ourselves. SARS, flu, MERS, Ebola, Zika, what's the next? The next, it could be HXAY flu. It could be after Zika, could be a Guka. Could be an Ethiopian car, whichever car. It doesn't matter what kind of car you have, but there'll be a virus there. Even if you use a backyard chicken, you don't have collect all those chickens together. They mix the chickens, meanwhile, mix the viruses. So that's what happened here. So once you get the live poultry market controlled, it's done. Rabies is another problem. You have a rabies, why you don't have a rabies in UK, in US, in Japan? Why? Why you have so many rabies cases in India, China? Human behaviors. You raise so many dogs, wandering dogs, on the street, in the rural areas. It's not well controlled. You don't vaccinate your dogs. You vaccinate the humans who were beaten by the dogs. Waste of money. If you eradicate the rabies, get the vaccine, vaccinate it to the dogs, not the human beings. It's so clear. But we cannot do this. So this is the very, give you a very example. This is both, and then ecology. So we used to live in a small area. We don't have so close contact with the bats, with the gorillas. Now we are so close. We are living together, one world. Now one world. We enjoy ourselves living together with those wild animals. Meanwhile, they brought the virus to you. So ecology of Ebola virus is a good example. We did a lot of work. I'll show you some slides. Intra-host evolution. Intra-host adaptation. You have a Ebola virus initiated maybe from mammals during an outbreak, for example, in Sierra Leone, now in Democratic Congo, Republic of Congo, in the border with Uganda. If you do the sequencing, you find any isolates from any individuals. The virus is adapting. You see the nucleotides changing. That's the beauty of sequencing. Sequencing is so beautiful. Sequencing gives you a vivid structure of the virus. You see the virus is adapting. So this is the ecology. What do you think about the influenza? Typical example, I'm not going to talk anything about the science for flu, for adaptation to the new host, from avian to human. Just single nucleotide mutation. They can change their tropies from avian to human. So, we published a lot of papers for that. That's exactly what happened here. No, so, one world, one health. We have to have the environment people involved. We have the medical people to be involved. We also need to get someone from agriculture. We do not fight each other. From time to time, anywhere, agriculture sector, medical sector, fight each other. We cannot sit at the same table. So that's a human-made problem. And then you think about the climate change, always there. When you think about it, you don't think human behavior never changed? It changed. Go back at home tonight, check what you wear. I don't want you to check here, but there's positive evidence. Human behavior change. You change your behavior. The virus also changes the virus behavior, right? So that's a positive evidence. You travel. I was in Beijing 12 hours ago. About 20 hours ago. I was on board, flying here, arrived local time 7 o'clock, landed here. Now I'm here. So this is the world we are living. We change our behavior. We are traveling everywhere. We are living in a small world, even a small universe. Everybody knows Elon Musk is sending someone to the Mars, to some other, somewhere in the universe. I hope still in the universe. Maybe one day he will claim, I'm going to send someone outside the universe. So where are we going? So this is exactly what happened here. So this is why ecology. Ecology, climate change, and plus the virus, plus the knowledge, the limitation of the human being's knowledge about the virus. So now, in this case, can we do anything? We eradicated, as I mentioned, we eradicated smallpox. We are so close to the eradication of polio. We eradicated the cattle, one of the cattle, myxoviruses, and we are ready to eradicate the polio. I hope one day in China we are ready to eradicate the hepatitis B. So we are so close there. So what we done because of the science. So I'm here calling for the investment for the science. Give the scientists enough money, give the scientists enough time, they will get a solution for you. So don't believe you wasted your money. Why we eradicated the smallpox? Because Jenner, just by chance, he found the immunology. He established the immunology and the immunity. Now we are doing so well for the immunology. Eradicated smallpox, nearly eradicated polio, quite close to hepatitis B. More importantly, with CAR-T, monoclonal antibodies, with the immunology development, we're so close to get the tumors out, almost immunology. So that's the investment for the science. So this I want to say you. So now I give you an example. Even people think electron microscopy is too high, that's high technology. No, it's so close. Once you know, so I'll give you an example. You see, that side is the virus. The virus in the middle, you will define how the monoclonal antibodies bind to the virus. So that beautiful, the red one is monoclonal antibodies, and the green one is the virus. Once you define this, you got a very good chance to do the reverse vaccinology, to design a new vaccine. That's exactly what people is doing now for the HIV. We are doing something for the HIV, reverse vaccinology. More importantly, we are isolated a lot of monoclonal antibodies. I'll show you later. And also surveillance. That gives you a very good example, Chinese National Influenza Center. So we are doing a lot of enhanced surveillance. Make sure any virus, before it comes, we know where it is, where they go, and how they come. So that's very important. That could give you a good example. NGS sequencing for the Ebola, this is exactly what we did. Remember, I remind you, during the outbreak of the Ebola in West Africa, in Sierra Leone, I was there between September to November. We collected, that's the sample number, and we sequenced that number, 175. We did the phylogenetic analysis, what we found, and this virus is evolved, but it's not in that state. They evolved like the flu. Now you think about why every year we need a new vaccine, because they mutated. In that stage, the old vaccine doesn't work. For this one, we did the sequencing. Sequencing tells you the Ebola virus in Sierra Leone, we sequenced, is still typical Ebola. The vaccine you developed from sequencing data tells you it will work. So that's the sequencing data surveillance can really help you for the prevention and control. It's not basic research. So this is the zero distance between basic research, between sequencing and vaccine development. That's a very, very good example. So this is, tells you dynamic evolution or adaptation. You see the Guinea virus like this. From May, September, November, you see a lot. I call this one shower chart. The virus evolved. You see all these mutations. From very Guinea virus down to November, you see a lot of new mutations. The virus came from some mammals, maybe bats. They try to adapt to the new host, human beings. All these mutations always there. And the usual host, Ebola viral adaptation, this paper is coming out soon. And the same, we did all this, we found the mutations. And more importantly, we did a follow-up for one of the females. We found, the vaginal fluids and blood, dynamic evolution. And also we found the HIV patient, the last patient with HIV in Sierra Leone. The HIV patient correlated very well with this Ebola sequence. So at that time, when I was there, me and my colleague, we wrote something to the science on the ground in Sierra Leone. We were calling for all the forces from the task force work together in West Africa. I'll show you later. Join me. We wrote something recently. We are calling everybody, join us. Let's work together. No one can work alone. No one can live alone. You got to work together. So the executive, we wrote something, for Sierra Leone, calling people to work together. Now, so for the vaccine, that's my research part as a scientist. Vaccine, immune, not drugs, sorry, it's immune biologics, like monoclonal antibodies. So that's a very good example. So that's my science part. As a scientist, what am I doing? So I'm doing this. This is a cell. You have a cell, you have a virus. So virus need to get into your cell to cause the damage. So on the surface of your cell, you have a lot of receptors. The virus need to find a receptor first, and then interaction. I'm doing some interaction. Here you have protein, ligand, protein interaction. This is my lab. I'm doing for this, all the different kind of viruses. And also, once the virus gets into the cell, your immune system immediately initiated. Once it's initiated, you have the protein be processed, presented out by MHC, HLA, recognized by your T cells. On that service, again, a lot of protein, ligand, protein interaction. I'm doing all this. Sometimes a virus like coronavirus, MERS, they can use a receptor on the T cell surface, like HIV, CD4. So anyway, so I'm working on the protein interaction. For that, if you work out for this, you can design some small molecule drugs, peptide inhibitors. You also can do some neutralizing antibodies. Now I want to focus on neutralizing antibodies. We did a lot of work. We published something for all this vaccine development. At the moment, I have a flu vaccine under development. I have for Zika virus. I also have a MERS vaccine under development. And monoclonal antibodies. We have very good platform at the moment. We can isolate by single cell sequencing any human monoclonal antibodies. This gives a very good example. This is the Rift Valley. We have a lot of Rift Valley human origin monoclonal antibodies. We are ready to collaborate with anybody, especially someone from the industry. Let's work together to get this produced, for the emergency use. That's Rift Valley. Then that's for the Rift Valley and also for the SFTSV. It's a new flammable virus found in China. Also monoclonal antibodies. And the monoclonal antibody for the MERS, we did all this and it works very well. And Zika. What Zika outbreak, we isolate many human monoclonal antibodies. This paper published in Science Translational Medicine as a cover story. I want to show you, Anyway, we have a lot of human monoclonal antibodies in my lab. We can collaborate with everybody. That's human for the H7N9. So human antibodies for the H7, we have a lot for the H7N9. More importantly, recently, we have a series of monoclonal antibodies against yellow fever. This is one of them. This is my collaboration with Hans Klenk. So we isolate one virus. The virus can stop the last model. They can bind to the virus surface protein. It's called old protein, E protein. In the two stages. One is a prefused stage, another one is an intermediate stage. That's a very good potent monoclonal antibody. So that's what we have. Cellular immunity, you want to increase the cellular immunity in addition to the antibodies. This is something we did. H5, anybody have the seasonal flu or avian flu, they have this background against all those T-cell immunity for the flu viruses. So this is what we did, H7, H3, and we cut a lot of story short. So I'm calling again. Last year, I was asked by the journal called Cell, can you write something to see the future to control the emerging pathogens? I wrote here, invest for the basic research. Do the surveillance. You get those jobs done, you'll be in the business. So that's my calling. So China CDC, we have a global health center. We are ready to collaborate with you. So this our president commit will build up the China Africa CDC. So the United States introduced about me, and we want to work together. Here's John and me. We were together this last year in Beijing. We took a picture today in front of that Mandela building. Remember, we are calling for the collaboration for all over the world. We wrote a comment in the Lancet Public Health called Public Health Priorities for China-Africa Cooperation with that picture in the journal. So we are calling for the collaboration, not just work together for the Africa and the China CDC. Everybody sitting here, everybody who's doing public health, anybody who has an interest for the public health, everybody who wants to do something good for this earth, unite, team up, work together. So to make sure the public understand what we are doing, I put two statues. One is flu virus, one is Zika virus, and in the campus in China, come to visit me, I'll show you this. And we made a World Flu Day. November 1st is a World Flu Day. Make sure people understand what you are doing. So if you did a lot of work, the public didn't understand, the politicians don't understand, it's a waste of time. The people, what are you doing, John? What have you done? So you make sure public understand, the politicians understand, then you will be in the business. So the future, One Health. Let's work together. One Health means health for everyone. Well, One Health means health. We need maintain health from environmental scientists. We need to have some agriculture sector, medical sector, peoples, and also the public, the politicians' commitment. Let's work together. That's my talk. Thank you very much.